In this video, we'll introduce a very useful tool known as the log likelihood variational bound. So in the previous video, we talked that we introduced the model deep belief network, and then I talked about the fact that this idea of pre-training neural networks by stacking RBMs actually came from deep belief networks. And then I tried to give an idea for how this was useful in the context of a deep belief network, where we would try to initialize a 3 hidden layer deep belief network by first training an RBM and taking its weights, first hidden layer weights, to initialize the sigmoid belief network part of a 2 hidden layer DBN, at which case we would keep those fixed to pre-train the second hidden layer RBM weights in the 2 hidden layer DBN. And then after doing that for a while, we would use the 2 first hidden layer weights to initialize the sigmoid belief network part of the 3 hidden layer DBN, and then we would be left with the procedure of training the top RBM weights of the 3 hidden layer DBN. And so to actually describe exactly how this procedure will come about and the actual details of the algorithm, we'll need a tool known as the log likelihood variational bound. And so in this video, we'll introduce what this is exactly. To introduce the variational bound, we will need exploit the concavity property of the logarithm function. So the logarithm function is a concave function, which looks like this. And a concave function has the following property. So if you take so let's just think about the log as our concave function. If you take the log of a weighted average of some numbers ai, where the weights of each ai is going to be this omega I here, and omega I is can be any weights as long as it's they're all greater than or equal than 0 and they sum to 1. Okay, so this is a weighted average of each of these numbers ai's. Well, the log of this weighted average for a concave function is always going to be greater or equal than the same weighted average, but of the logarithm of the numbers ai. So visually, if we had two numbers, a1 and a2, then what this would correspond to is that the weighted average between the log of a1 and the log of a2, so which corresponds to this line here. So this line is the weighted average between log of a1 and log of a2. So log of a1 is here, log of a2 is here, and so any weighted average would fall between the straight line between these two points. So that line is always going to be below the logarithm of that function between a1 and a2. So the logarithm, in other words, of any weighted average between a1 and a2 using the same weights. Okay. So that this is visually we see that for a concave function we always get this. We get that this line would be below the actual function. And so that's what this property refers to, but for any number of points, not necessarily just 2, but any weighted combination between any number of weights of numbers. So that's an important property that we'll leverage to get our variational bound. Okay, so the idea of a variational bound of the log likelihood for some model is actually very useful for a lot of graphical models with latent variables. So imagine we have any model, p of x and h1. I could have written just h to be general, but we'll use it in the next slides, in the next video, for the specific case of the first hidden layer in DBN. But any model that defines a distribution over x using some latent variable h1 is going to have the following variational bound. The idea of the variational bound is to take the log likelihood, which might be too complicated to compute. So log of p of x would require summing over h1, and there are some models if there that might be too complicated in the interactions between x and h1, or in the number of values of h1, to allow for performing that sum exactly. So instead, what we'll derive is an expression where we've added these new parameters, this sort of separate model, if you want to think about it this way, which we call Q of H1 given X. Q of H1 given X is sort of a separate model. And you can think of it as an approximation of what would be the true posterior under our model, P of H1 given X. So Q of H1 given X can be different from P of H1 given X. It has a separate set of parameters. And by introducing these extra variables, we'll actually be able to formulate a lower bound on the log likelihood. And this lower bound will have certain properties that are interesting for if we wanted to actually optimize this log likelihood. We could then optimize instead the lower bound, and by pushing the lower bound up, we can hope that we're also pushing the actual log likelihood up. So that's the idea, the main usage for the variational bound that we often see in the literature. Okay, so how do we actually get this lower bound? So we have that log of P of X is equal to this expression here. So let's go into 2 steps. So first, ignore this term here and this term here. So what this is saying is that the log of P of X is the log of the sum over H1 of P of X and H1. Okay, so we're marginalizing H1, so that gives us P of X, so that's equal. And now what we're doing is that we're just introducing this variational model or posterior Q of H1 given X by multiplying and dividing by it. Okay, so these would normally cancel. So that's why we haven't changed anything, so that's why we have the equality. And now we're already ready to use the property of concavity of the log function. So by using those, considering those as our weights, and those here, the ratio P of X and H1 divided by Q of H1 given X as our numbers AI, then we can exploit the concavity of the log by saying that this is greater or equal than the weighted average. So we're summing over all values of H1 weighted by Q of H1 given X of the log of this number here. So the ratio P of X and H1 divided by Q of H1 given X. Okay, so this here we can think of it as a huge weighted sum over an exponential number of values of H. If we think of an RBM, for instance, where these are binary and they take so globally they take 2 to the number of hidden units values. And so now this weighted sum, we can obtain its lower bound by doing the weighted sum instead of the log of the ratio here. And now exploiting the fact that the log of a ratio is the differences of the logs, then we get that this whole expression here is just the sum over H1 of Q of H1 given X log of the numerator here, P of X and H1, minus the sum over H1 of Q of H1 given X times the log of Q of H1 given X. Okay, so we just almost straightforwardly exploited the concavity of the log function, and that gave us our lower bound on the log probability under a model P of X, which is lower bounded by this expression here for any choice of what Q of H1 given X is. And that's because for any weighted average this is true. So these are the weights of our average, or for any choice of our posterior, approximate posterior Q of H1 given X, we have this, that this is greater or equal than this whole expression here. So this is called the variational bound or variational lower bound. So I just removed that what was in between this and this whole expression here. One property of this variational bound is that if our separate posterior Q of H1 given X is actually exactly the same as the true conditional in our model, P of H1 given X, then we actually have an equality. So this would be equal. So let's do a very quick and dirty demonstration of this. So log of P of X and H1, we can write it as the log of P of H1 given X plus log of P of X. So that's because P of X1 and H1 is P of H1 times P of H1 given X times P of X. Then if we take the log of that, that's just going to be the sum of the logs. Now, we're considering the case where Q is exactly the same as P, so we'll just change the Q's to P's. And now we notice that we have the sum over h1 of P of h1 given x times the log of P of h1 given x. And then we have minus exactly the same thing here. So this term would disappear with this one, would be cancelled out by this one. And now we just have sum over h1 of P of h1 given x times the log of P of x. Well, the log of P of x does not depend on h1, so we could actually put it right in front of the sum. And then we'd sum over just P of h1 given x, which would be 1. So we would be left with just log of P of x, which is exactly this here. Okay, so that's a very quick and dirty demonstration that for Q of h1 given x equal to P of h1 given x, we actually have an equality. And just generally, the more Q of h1 given x is going to be different from the true posterior, then the less tight this bound will be. The bigger the difference between this and that whole expression is going to be. And in fact, the difference between the left and right part of this bound here is going to be the something known as the KL divergence between Q of h1 and P of h1, which is this expression here. So in general, the KL divergence is, you can think of it as a kind of distance between distributions. It's not a distance because it's not symmetric. If we change the order of these two arguments, we get different numbers. We can get different numbers. But we see that, for instance, it's 0 if Q is equal to P. So in this expression, if we have P here and P here, then this cancels out with that. So we get log of 1. Log of 1 is 0, so all the terms are going to be zeros. Okay. So what's interesting with the variational bound is that it suggests a procedure for optimizing the log probability of our training data, even if we have a model where we can't compute that term exactly. And the approach we'll take is to try to instead work with the lower bound and try to push up the lower bound. And the way that this is usually done is that we would first, at the first step, we would try to find our approximation Q of h1 that is as close as possible to the true posterior. So we would optimize the KL divergence between Q and P for some family of models for our posterior Q. And then once that's done, then we will keep Q fixed and we'll actually optimize with respect to just the log of P of x and h1. And if we make good choices for what this approximate posterior here is, then it turns out that for certain cases in certain models, we actually can much more easily optimize this expression here. So then we alternate, the algorithm would be alternate between updating Q and updating P. Updating Q, updating P, and you do this until convergence. And so by doing this, so when I say updating, we say maximize this expression with respect to Q and then maximize this expression with respect to P, and then alternate until convergence. So by doing this, we push up the lower bound. So we're ideally, we can hope that we're actually pushing this. And also the EM algorithm is based on this idea, but where at the E step, it corresponds to finding Q, which is exactly equal to P, if you're familiar with the E step. Okay, so that's why I'm talking about it here. It's a very, very useful tool in general for training probabilistic graphical models. And we'll also use it for, in the next video, for deriving the greedy layer-wise pre-training procedure for a deep belief network.